My name is Wayne Huang, just in case you have not remembered my name. Dr. Wayne Huang. You can call me Dr. Huang, and I'll be teaching this course for this semester. All right, last time we explained the syllabus, right? And I was supposed to do a little quiz afterward, but I didn't have time, so I'm gonna do it now, all right? And just relax, this is just a fun thing to do. No credits for this, just some class activity game, okay? And since you're not here last time, you can just go with the flow, no stress, all right? So quiz number one, question number one. How many, let me see, oh. How many ways are there to earn bonus credits? All right, so I'm gonna have 3 different answers. 2, 3, sorry, 2, 4, and 6. All right, so I would like you to stand up. If you remember what's written on our syllabus, you probably know the answer, and if you don't, just guess. Take a wild guess. If you think there are 2 ways to earn bonus credits, stay in this aisle. And if you think it's 4 ways, stay in this aisle, all right? So, move.
I think it's a trick question.
A trick question? So, 2? Are you standing for 2?
I was so sure it's 3, so I'm just
3. All right. How about you guys? 4? 3? Then you should stay with her.
I think 4.
4, then you stay with her. How about you? 3, then you stay in this line. Right, since nobody liked 2, I will just change this to 3 to make some room. Now you guys can move. How about you guys?
I think it's more than 4, but I'm not sure.
4?
6. I think it's more than 4, but
More than 4. Well, you don't know. Standing on aisle 6. How about you?
also
6. All right. See, we have a normal distribution. That's awesome. That just shows that the information didn't get in. All right. So, okay, I just assume that you guys think it is 6. Okay. All right. Now, what I'm gonna do next is I'm gonna want you guys to try to just grab one random person next to your line and convince her, or him why your answer is correct. Okay? Okay, I'll give you 2 minutes.
Okay, so
All right.
it's easy. There was no 3 before, so it has to be 4 or 6. And at first he put 2, 3, and then something. And he thinking, okay, there's no 3, so let's put it. So it has to be 4 because it goes next.
Hey, you guys need to talk to people who have different opinions. Okay?
Sorry? Because 6 is too much.
I don't know.
Do you remember what he at first? He does. 2, 3, and something. But so this is the maximum of what he thought at first.
No. That one's not in the syllabus, but like on the website, there's many documents, right? And one of them are syllabus and manual and something like that. And one document is the title of 4 ways to earn bonus. Yeah. So in my family, teachers are missing, so that makes it more confusing. Yeah. Have they never never?
I mean,
How long have you studied? 4 years. They never been wrong. It depends on the teachers and as you said, this teacher seems like the one that you seem to be very serious about this.
All right. I think it's almost time. So I need you guys to choose your answer again out of your own will. Please choose again. And
Not as a group.
not as a group. No, individually. Yes, you're on you are your own master.
Okay. 5 and 3 is the good choice. I think it was.
Okay. How about you?
Take many notes.
3,
four.
4. Okay, you're entangled. I see. How about you?
4 or 5.
Okay. How about you?
Still
6.
6. Yeah.
All right. Well, you need to make up your mind. Okay, 4 or 5.
4.
Okay, stand. All right. So now,
It's a perfect fit.
now see we have a sharper delta distribution. All right. So the answer is 4. Okay. Thank you very much. Please sit back. Thank you.
So you're not a messy person. That's good.
I'm not. I'm not. All right. I'll just quickly remind you that there are 4 ways. The first way is to do a bonus objective. Okay? Bonus objective, and this is only limited to quantum spin lab. Okay? Second is, I believe, essay. Okay? There's an essay to write. Optional. Third way is, bonus. No, actually, second is the bonus lab session at the end of the semester, at the final week. Bonus lab session. And the third is essay. And the fourth is how you work in the lab, collaboration. Okay. And for collaboration, we have 3 roles. So it's like a role play game. They are writers, analyzer, and experimenter. Okay. In case of you have only 2 people in the group, the writer will also be the analyzer. Okay. So writer, analyzer, and the experimenter. All right. I'm gonna just also remind you that this is 1 point per bonus objective. Okay? So this is 5 points just for participation. You don't need to submit a report or anything. Just being there will earn you 5 points. Essay is also 5 points. Okay? So 2 readings. And collaboration is 1 point each person per lab session. Okay? So I want you to do a real quick calculation. We have in total 14 regular lab sessions, right? So how many points you can earn, like maximum point you can earn from here? Collaboration. That's 14, pretty easy, okay? Well, if you spend, I would say, 4 hours, including reading and writing on this, that will give you 5 points. And if you come to the lab session, that will also give you 5 points. And say, if you just do 1 bonus objective per spin lab experiment, and we have 7 of them, you will earn 7 points. So together, that is, wow, that's pretty amazing. That is 31 points in your final grade. Okay, so that's a lot. That's equivalent, that's more than one report. And you're only allowed to write 4 reports. So that's like the extra 5th report. Okay, and so I hope you could take advantage of this. All right. There are also more informations. Some of them are on the syllabus, some are not, on eLearn. I encourage you to take a look of our eLearn website. Does everybody know what that is? eLearn website. Yeah, eLearn. It's called eLearn. If you don't know what that is, ask person next to you how to get there, or Google eLearn NTHU. And you just need to, if you register for this class, then log into your university account will allow you to access all the course material on eLearn. Okay.
That is something different than e-class.
That's different. This is sort of just a website that collects information, like your grades, your course materials, important announcements. Yes.
The thing is that we exchange students a lot of the information that we're supposed to report that information on eClass. But so my question is only, because I have 3 different ways. It's like some teacher has their own website, and then there is eLearn, and then there is eClass. Is there like another extra system for the school, or is eLearn and eClass the ones?
I don't know about eClass, to be honest with you, but eLearn, I'm sure you already seen that, right? eLearn is the website I put all the information on it. Okay, so yeah, I encourage you to take a look there for our class materials. All right, second quiz. I'm doing this because this helps. Second quiz. So last time we talked about particle wave duality, right? Okay, you were not in this class. You were not in last class before, but we have the recording, lecture recording. So if you want to take a look, you're welcome to. The link, the lecture recording link is also on eLearn website. Okay. So say, second question is when a matter is in the quantum regime, does it behave more like a particle or a wave? Okay. All right, so this is the second question. So again, after we're done with this, we're gonna start with our today's lecture. But I think a little recap is good for long-term health. Okay, so pretty easy. 2 options: particle, wave. All right, so when the matter, keyword matter, is in a quantum regime, does it behave more like a particle or wave? Choose your aisle, please. Wow, I guess everybody agrees. All right, well then, thank you very much. Please sit down. We don't have anybody sitting on this side. All right, yes, correct. It is wave. Okay. But when energy, like electromagnetic wave, when energy is in the quantum regime, it will behave like a particle. Energy and matter are opposite. Okay. Okay, today we're gonna have a pretty long lecture about nitrogen vacancy center. Nitrogen vacancy center is, I believe, the first room temperature qubit that people have found. In the past, if you would like to see any quantum behavior, you need to have very special condition, such as high vacuum or low temperature. But nitrogen vacancy center is the only, well, as far as I know, it's the only quantum system that can operate at room temperature and ambient condition. That's why we're using it for our teaching lab. Yes. Ambient means air. No special vacuum system to isolate your quantum system from other things. Okay. So this is pretty cool. So I just want to give it a quick note that the feature of this is room temperature. And ambient condition. Ambient condition. For this qubit to operate. Of course, if you put it into vacuum or lower the temperature, it will help its performance, but it's not critical. It's not necessary conditions for it to work as a qubit. Yeah. All right. So today we're gonna talk about how this magic happened. All right. So to be more precise, it is not just nitrogen vacancy center. It is nitrogen vacuum center in diamond. Okay. So diamond, being the host material, has we know diamond has carbon atoms, right? And it looks like this. In the three-dimensional structure, it looks like a pyramid. We don't have a pyramid here, but basically, one carbon atom will have 4 legs. Yeah. So 2 legs like this and 2 legs like this. Okay. So this is like in the back. Okay. So this is 1 carbon atom and will link to another 4 carbon atom, and every carbon atom will link to another 4 carbon atom like this, and together they form the diamond structure. Okay. Now, from our elementary chemistry, we understand that carbon atom has how many electrons? That's a good answer, but not correct answer. Carbon atom has, we know carbon has 6 protons and 6 neutrons, right? So in total, it has 6 electrons to match with the proton. Now, on the periodic table, we have, right, like this. Okay. No. Sorry. So we have helium, we have hydrogen here, we have helium here, right? And then carbon is 1, 2, 3, 4, the 4th on the second row. Okay. And so that shows carbon atom has in total 6 electrons, but only 4 are free. Yeah. So this is the nuclear. And in its innermost electron orbits, there are 2. And these are basically buried in the core. And they are combined so tight by the nucleus they cannot move. So they cannot participate in any chemical or physical interaction, right? On the outer shell, there are 4 electrons. And these are free, relatively free. And they can participate in chemical reactions, bondings, or physical, they can respond to physical excitations. Yeah, all right. These are called the valence electrons. Valence electrons. So you're right, carbon has 4 valence electrons and 2 core electrons. Okay, and valence and core just describe their position. If it is in the outermost shell orbit, then it's called valence. Otherwise, it's buried inside and it's called core. Okay, core electrons 2. All right, so we know so I'm gonna just draw 4 electrons for carbon because only 4 are free to participate in bonding with other atoms. So each carbon has 4, right? And this one also have 4. And when this one is also have 4. This one also have 4. Okay. I'm going to just draw every valence electron. Okay, now when there are 2 electrons between the atoms, they share the same orbital and they form a bond. Okay, so this is a bond, this is a bond, this is a bond, this is a bond, this is a bond. Okay, that's how chemical bonding works. All right, so just in case you don't know much about the chemistry of carbon atoms, this is just a recap. And now, when something interesting now in certain occasions, you could have let me just fill all these bonds with 2 electrons. So in a perfect diamond, you have this structure, okay? And the chemical bond between each atom has 2 electrons. Now, in rare occasions, you could have a vacancy. A vacancy means a missing of a carbon atom. Okay, and in that case, the bond does not exist no more. There's no bond. Okay, because it requires 2 electrons to form a bond. So no bond. And this electron just being free. So this 4 electrons from the surrounding carbon atoms, which is supposed to bond with the atom in this position, now have no partners to bond with, so they have become free. They are called the dangling bonds in the literature. The dangling bonds. Okay, and this name just reflects the nature that they are kind of just being there, and they are ready to grab or interact with anything that comes nearby. Okay. All right. So we call this vacancy, and we give it a name V. Yeah. Now, also occasionally there are nitrogen atoms buried in a diamond because we have we have abundance of nitrogen in air, right? So it's probably not a surprise that occasionally we will have nitrogen atoms buried in the diamond structure. And let me just, for the sake of let me just use this one. Okay, so let me just take the bounds away for now, and see what happens when we have a nitrogen substitute or replacement. Yeah? Nitrogen, orange. Okay, how many atoms? How many electrons does nitrogen have? Yes, correct. So carbon has 6, nitrogen have 1 more, 7. Yeah, and remember, just like at carbon, the first 2 are buried in the core orbitals, and only 5 exist. So this is carbon 12, and for nitrogen has 14. So 7 protons and 7 neutrons. It has also in its core 2 core electrons, but on the outer core, on the outer orbital, it has 5 instead of 4 valence electrons. Okay, and this is very important. Valence electron 5, and core electron 2. Now, so when it is here, it has 1, 2, 3, 4. It provides the necessary 4 electrons to bond with the neighboring carbon atoms. That's okay, but it has 1 extra one. That is just 1 extra one that just hang there. Also a dangling bound, yeah, because nobody is using it, so it just kind of dangle there. Okay, so this is what you need to know for basics. Now, so in the very rare occasion, we have a vacancy, which will give us 2 free electrons in its neighborhood, which will have 4 electrons in its neighborhood. And also in the rare occasion, we will have a nitrogen substitute, and that has 5 electrons. 4 participate into bonding, and 1 is free. So I'm gonna mark it with blue. Yep. Okay. In the even more rare occasion, the nitrogen and the vacancies are adjacent to each other. In general, they are randomly distributed on the lattice. Okay, so it's just like you and him. Typically, you are randomly walking in the campus. You don't see each other, but very occasionally you meet, maybe at the restaurant or the library, right? So in the rare occasions when the nitrogen and vacancy are adjacent to each other, something magical will happen. So let me just draw this again. Okay, it's a very big array. So vacancy and nitrogen. So what will happen is, by the way, there's no bond here, there's no bond here, there's no bond here. So I'm just gonna draw this free dangling bonds, okay? Two, 3, okay. By the way, since they are adjacent to each other, now it has only 3 electrons participate into bonding, and 2 are free. So instead of 1 is free, it has 2 free electrons. Okay, so again we have 5 free electrons. Now the magical thing happens. These 4 electrons, together with the nitrogen atom, this will form a molecular-like structure, become an NV molecule. Okay? Oh, no, not molecular. Okay. So it has molecular-like orbitals, and so they are just like regular molecules. They bond together. All this bond with the nitrogen in the way that it looks like this MV is a big molecule. Okay, and people call it MV center. The formal name is MV center. Okay. All right. This is called the neutral charge state. All the participating electrons are intrinsic. Okay, are intrinsic. They are from the atoms that are in this molecule. Yeah. But occasionally, remember when we have a nitrogen that is surrounded with carbon atoms, you will have one extra free electrons, right? It's here, right? So occasionally, these free electrons will get captured into the molecule and make the molecule charged. Okay, so it's a charged state, and in that case, we call so there are two states. One is without an external electron, and that's called MV0, neutral charge state. And the other one is MV minus, the negatively charged state. Okay, and that is when a neighboring nitrogen atom is present and its free electron gets captured by this molecule. Okay, so instead of being a neutral molecule, charged neutral molecule, it will be a charged molecule. Okay, now depending on the host material, the condition of its environment, sometimes this is more stable, sometimes this is more stable, right? For our purposes, in our teaching lab, we use the MV center diamonds where the MV minus state is more stable. Okay? Just so you know, both exist and people have used both to do experiments. But for our purposes, we use this one. Okay? MV minus. But from now on, I will not emphasize on the charge minus sign here. I'm just going to say it's MV center. But just keep in mind that this is what I'm talking about, the negatively charged state. All right? All right, good. So now let's talk about the electronic structure. The electronic structure of this MV molecule. Let's see. Yes. We know diamond is an insulator, right? Diamond does not conduct electricity. Diamond is an insulator. And the reason it is an insulator is because it has a huge band gap. Huge. Okay. Normally, in the semiconductor, so if you never heard of this word band or band gap, that's okay. Just know that when atoms form a solid, their energy level no longer remain discrete. They become continuous. Okay, and just like in the individual atomic states, the ground state is where all the energy are in the lowest energy configuration. Okay, and that's called for solid, it's called valence band. Okay, valence band. Okay, and these electrons are basically the electrons that participate in bonding, or mostly non-mobile. So they kind of just like fixed, trapped near each atomic site. Their excited state is called conduction band. And when there is an excitation, either from a laser or voltage, electricity, you can excite electrons from the valence band to conduction band. When they are in this band, their orbital, means where they can move, is very localized. Okay? But when they are in this band, their orbital is very spread out, very non-local. Okay? So if you can manage to get electron to this band, then you have conducting electrons, and your material can conduct electricity because the electron can move. Okay? And the reason insulator cannot conduct electricity is because there's a huge energy gap between the valence and the conduction band. Okay? Normally in a semiconductor, this band is around, I'll say, maybe 2 eV. Okay? In a semiconductor. So that's a reasonable size, but not huge. This can still be overcome by applying voltages or shining laser light to it. Okay? But for insulators, such as diamonds, this band gap is 5 eV or even more. Okay? So it's huge band gap. So it's really difficult to get electrons from the valence band to the conduction band. Thus, it does not conduct electricity. Okay, so that's the basic idea behind conductions. Now, when there is this extra molecule present in the diamond structure, what will happen is there will be discrete states that does not participate in this bands. Okay, they are kind of isolated out because they do not belong to this gigantous ensemble of carbon atoms. Okay, they are special, and since they are special, they are kind of isolated out. And typically, experimentally, we found that they will exist. This energy, this electronic states from such MV centers or any defect, as a matter of fact, the energy will fall into the range of this gap. Okay, and they will remain their discrete nature. Okay, so instead of being continuous, they are discrete. Okay, so this is almost saying like if you bury an atom that is different from its host material, that atom will still remain its atomic property. It's basically saying that. Okay. Okay. So, and the reason I drew this full picture is because I want to tell you the following. I'm going to erase that. The MV center electronic state looks like this. Okay? This has, all of them have their name that does not make sense to us or me. But let's just take it as a symbol. Okay? A, B, C, D. All right. For MV molecule, it has two lower energy states and two high energy states that are degenerate. Degenerate means the same in energy. Now, it had for MV minus, how many electrons do we have? 6. We have 6. 6 electrons that is participating in the bonding of the molecule. Okay, just see this as a fake atom, a virtual atom. Okay, and they are bonding with each other. Okay, and these 6 electrons are participating in the bonding. 6 electrons, 6 valence electrons. Okay, you can almost say that it's valence electrons. Okay, now if we have 6 electrons, how are they gonna fill the states? If we know, if you ever take modern physics, you probably know that there is something called Hund's rule that tells you how electrons are supposed to populate atomic states, right? Now, the rule of thumb is they will try to stay low as much as possible, okay? If they are a degenerate state, they will feel this first before they move to higher energy states. That's rule of thumb number 1. The second is when electrons are in the same state, occupying the same orbital, moving in the same way, they must have opposite spin direction. Okay, this is dictated by the Pauli exclusion principle. So when they are occupying the same state, they must have opposite spins. Okay, and suppose you have a atomic structure like this, and you have 6 electrons, right? After you fill in the first 4 on the lowest state, now you have 2 more, and they are free to occupy any of these 3 because they are energetically the same, right? Guess what the electron will do? This is like a bus. When you and your friend, not you and your friend, when you enter a bus and there are 3 seats, okay? And there are 3 of you passengers. How will you pick your seat? There are 6 seats, okay? 6 seats, 3 rows, okay? How will you pick your seat? You will try to stay as sparse as possible, right? You would like to have your own seat. So are electrons. They like to have their own seats. They don't like to share. Yeah? Okay. So when they have their own seats, they're happy. This is Hund's rule number 2. Okay. So just remember these are the 2 most important rules when electrons are stay in their ground state. Now, in this case, we have also 6 electrons. Okay. So guess what will happen? In the ground state, in the lowest energy configuration, of course, we're going to have this field completely, right? That takes already 2 out of 6. And then this is the next energetic state. So we're going to have this field too, right? So that takes 4 out of 6. Well, and of course, these This has spin opposite each other, yeah? And then we have two more. We have two more. What will happen? That's correct. You are listening to the lecture. Yay. Sweet. Now, and energetically, I mean, yes, the electrons likes to be in this state, but energetically, it is the same as this configuration, right? Yeah.
I have a question. Or two, in this one, don't we still have 7 electrons, or what are we talking? What is this system?
So this is the MV center. So this is the MV molecule. 7. Where's?
In this configuration.
Oh, this is just an example. I'm sorry. Yeah, so I'm just using this to explain Hund's rule. Okay, so I'm going to erase that to avoid confusion. Yes, we have 6 electrons, correct? And these are the energy states that we need to feel. Yes.
Why can there only be 2 in each?
Oh, that's a good question. Why can there only be 2 in each state? Okay, that's actually a very fundamental question. It's called Pauli exclusion. And I'm not just gonna give you names. I'm gonna explain it. Pauli exclusion principle. The reason we call it principle is because nobody knows why. It's like the law of gravity. Why does matter gravitate to another matter? Gravitational law. Anybody knows why? Yes. Einstein explained that is because mass bends space-time structure. But why does mass bend space-time structure? Nobody knows why. Okay? So that's why we call it law. And the same thing with principle. When we have a principle, when we call something a principle in physics, that means we don't know why. It just worked that way. Okay? So Pauli found that Wolfgang Pauli is a very, very famous physicist, theoretician to be precise. So he found that electron being he found that there are 2 types of particle in this world. 2 types. All particles can be categorized into either this one or this, A or B. The first one is called boson. The second one is called fermion. And how are they different? They are different in their, I'm not going to explain this, but I'm just going to give you names now. They are different in their quantum statistical properties. Quantum statistical properties. For fermion, they are governed by Fermi-Dirac distribution. Okay, if you like, you can Google or wiki this name, Fermi-Dirac distribution. And boson, they follow the Bose-Einstein distribution. Okay, and not the qualitative difference between these 2 is fermions do not like each other. They cannot be in the same state. One fermion cannot be in the exact same state as the other fermion. Okay, so the quantum state has, we have not talked about quantum state, but just think of it as a tag, a property of a person. Okay, like I am wearing blue shirt today. I am a male. I have short hair, right? my height is 177 centimeter, right? I weigh 90 kilogram. So these are my properties. These are my tag, right? This describes my states. For quantum particle, they also have many different tags, okay, like labels. And this label together define the identity of this quantum particle, yes? Pauli found that no two fermions can share the same identity. They cannot have the same quantum states, okay? They cannot be the same. But for boson, they love to be the same. Oh, sorry. Let me just use this dash arrow. They don't like to be the same. For bosons, they like to be the same. They like to be like each other. They are imitators. They like to imitate their neighbors, okay? And let me give you an example. Photons is boson. So they like to be each other, be like each other. And that's how laser works. The reason laser is so directional is because every photon wants to follow in the same direction. They are very collaborative. They are like sheep. Sheep like to group together, okay? But fermions, electrons are fermions. Fermions are like wolves, lone wolves. They don't like to, no, sorry, not wolves. They're like lions. They don't like to be around another lion, okay? Each electron just want to be his own king, yep? So that's what fermions do, and that's what bosons do, okay? So since electron has only 2 degrees of freedom, one is the motional degree of freedom, that's how you move. And the other is the spin degree of freedom, okay? So that's like a hat you wear, blue hat or red hat, yeah? So since there are only 2 degrees of freedom, and in quantum mechanics, we usually use this symbol called broad-cat notation. We use this symbol to just represent the quantum state. It's a symbol that people invent almost 100 years ago. Okay, there are 2 tags. One is motion, and the other is spin. Okay, what is spin? There is really no fundamental understanding of what spin is. We only know that it is a property associated with particles that dictate its statistical behavior. It's not something that is physically spinning, okay? People will make an analogy of that, but that's really not how it works. It does have a lot of properties shared with angular momentums and or a top. But anyway, just know that there are 2 labels, 2 properties of an electron, spin and motion. Now, these states represent motion, yeah? So in this case, your motion can be A1. You have 4 different options. A1 prime, A1, EX, EY. That's the states available for you to choose from, for this electron to choose from, yeah? And the spin, there are 2 spin states, up and down, available for electron to choose from, okay? So if 2 electrons choose already the same motional states, which is this, what degree of freedom do they have left? The spin. And they must have opposite spin. And this will allow them to occupy the same orbital but have different spin because now the total quantum states are still different, right? Can you have a 3rd electron here? Answer is no, because you run out of the spin degree of freedom. You only have 2 options for your spin. The 3rd electron will either have spin up or spin down, but that will make it have identical quantum state as the existing electron here. So therefore, the law of nature dictate that a third electron cannot occupy a motional state. Okay, so I hope that's clear. So now let's come back to this. We already we said that there are 4 electrons in the occupying the lowest 2 motional states, right? And there are 2 left, and these 2 are free to take these 2 degenerate motional states. And when they are here, they definitely they will have to have opposite spin direction, right? So they could be either here, or they could be either here, yeah, or as Clement says, they could be here and here. And in this case, they could have opposite spin or the same spin, right? So these are all the possibilities that could happen, yeah? But now, okay, let me just erase this. Yeah, sure. Okay. So what will happen? Out of this many possibilities, what will happen? Okay. The answer is that Hans rule dictate. So indeed, what we see, what we observe from the experiment and also according to theory, this is occupying 2 separate state will give the lowest energy configuration. Okay, so in principle, you have. Let me just. I will. For now, I will just ignore this 2. Okay, so this. So the first state that will show up, that will turn out to be physical, is a superposition of 2 electrons in separate states having opposite spins. Okay, what does superposition mean? Superposition means having 2 identity at the same time. If I am in a superposition, if I'm in a superposition of position states, okay? So say here is a red chair. Here is a blue chair. Classically, a particle behave in the classical region, a particle such as the electron behave like a particle. So classically, the particle can only sit in this chair or this chair, but not both, right? Classically. But in the quantum region, a particle behave as wave, and the wave can spread out, right? And a wave spreads out, it's not localized. So a wave can occupy 2 positions at the same time, okay? And this is called superposition. If you occupy 2 distinct states at the same time, then you are in the quantum superposition. Yep, that's just the terminology. Superposition means you're occupying two states at the same time. And when people take a measurement, like 10 measurements, you will appear sometimes here, or sometimes here, or sometimes here. And depending on your predetermined probability distribution, because in a superposition, you can still have unbalanced weight. Like you can have like 70% of time sitting in this chair and 30% of the time sitting in this chair. It doesn't have to be half-half. If that is your superposition ratio, then taking measurements for multiple times will find you 7 out of 10 or 70 out of 100 measurement being show up in this chair. And the other 30 times we will show up in this chair, okay? Yes? So that's how superposition work. And this is an equal ratio superposition. So an equal ratio superposition is what turned out to be the ground state, okay? And they were also, since these two are degenerate, it doesn't, as long as they are in separate orbitals, it doesn't really matter how the spin orientation, right? So there are also this one, and there are also this one, right? So 1, 2, 3, right? Theoretically, they all have these three configuration all have the same energy, correct? So this is what is called triplet, because they all have the same energy. Okay, triplet, and since they are the lowest energetic configuration of the NV molecule, they are called the ground state triplet. Okay, they are called the ground state triplet. Triplet refers to their spin orientation, the spin configuration, and notation-wise, we write this like this. Yep. Okay. So supposed to have the same energy. Okay. So spin triplet, and I'm just gonna give it a name. M equal to 1, M equal to 0, N equal to 1, and N equal to -1. Okay, I would not explain the meaning of this name for now. I'm just using it as a label. N equal to 1 represent this state. N equal to 1 represent up. N equal to -1 represent down. Yes? Okay? Okay, so supposedly you have three states, three configuration. So this give you, there are three configuration, -1, 0, and +1. These three configuration all have the same energy. Yes. Right. Now the interesting thing happens. Now, do you know that a magnet is made out of tiny spins? Okay, so what is a magnet? A magnet means all the electron spin in the solid are aligned in the same direction permanently. This is called ferromagnetic magnetic. Okay, so a permanent magnet is a ferromagnetic material, and all the electron spins are aligned in the same direction, and that gives it its north pole and the south pole. Yeah, and you know that this, from a magnet, you have the magnetic field, correct? And the magnetic field direction goes like this. Probably have seen this picture, right? Because Earth itself is actually a giant magnet, and it has the magnetic field. Earth has its own magnetic field, correct? Now, if we reduce this picture down to its very fundamental unit, it's not hard to imagine that each spin, being the fundamental unit or basic unit of the magnet, also have a magnetic field associated with it, right? So each spin has a magnetic field associated with it. A tiny one though, a very tiny one. Okay, so this is called spin. Okay. And when the direction change, the magnetic field also change with it. Yep. Together, all the magnetic field of all spins together sum into this this effective magnetic field of the magnet. Yep. Now, in the presence of one electron's magnetic field, another electron is tend to align with the magnetic field. Just like another magnet, when you put another magnet, right, it will seek its lowest energy state and have its north pole align with the south pole, and the south pole align with the north pole, right? The same with electron spins. When two spins are close to each other, they will, under the influence of the magnetic field of one electron spin, the other electron spin will tend to align with it. And this will be the low energy state. Yep. If it is not along, if it is not along the on the magnetic field, if it's opposite to the magnetic field, then this will give high energy states. Yeah. So you can remember from this argumentation, the conclusion is when two electron spins are sitting close to each other and they have the same direction, that is a high energy configuration because of this magnetic field from each other. That's a high energy configuration. When they're opposite, that's a low energy configuration. All right, so with that knowledge, let's come back to this picture. Yeah, you see? This one electron and this one electrons, they have opposite spin orientation, right? And they are in a superposition. The other say has also opposite spin orientation. So this will clearly give the lowest energy. This will clearly have the lowest energy state. Sorry, not energy state. I mean, this will clearly have a lower energy than this, right? Because this has the same, the electron spin are in the same direction. Yep. So this will have higher energy than this configuration because of the magnetic interaction. And how about this guy? Do you think this will have the same energy as this or a different energy? Not a quiz. is this going to have the same energy as this, or it will have a different energy? If different, will it be higher than this or lower? Same. Same.
Is there any external flux?
No. Okay, yeah, correct. Answer is same. This will have the same because putting two magnets in the same direction, it doesn't matter if you flip them like this or put them like this, it doesn't really matter if there's no external magnetic field, correct? Okay, so they have the same energy in the absence of external magnetic field. Very good. So this picture now, after taking into account of the magnetic field, magnetic interaction between the spins, the degeneracy now gets split. Okay? Okay, they were supposed to be on the same line, but now no. Relatively, these two will move higher. Because of this interaction. Okay? Yes. All right. So the ground state triplet has 3 states, and the 3 states are split into 2 energy scale, not scale, 2 energies. One is lower, that is n equal to 0, and the other 2 are higher, and they have the same energy. Yeah. And the splitting, the difference here, in terms of photon energy, it is h bar times 2 pi times 2.875 gigahertz. Okay, and since these two are constant, usually we just not pronounce them. Okay, so this is a Planck constant. So for photons, Planck constant times frequency is the photon energy. Okay, so if you want to try to excite this with electromagnetic wave with photons, you need a photon with such frequency so that the energy, the photon energy, will be enough to help the electron make a transition from this configuration to this configuration. Okay? All right, so now we have laid out the foundations of our discussion. Now we can really discuss our experiment. Awesome. This is not easy, but you manage to stay awake. That's pretty cool. All right. One more thing, just before I erase this. Now you know that the MV center has such energy configurations. I want to just draw a more precise picture here. So more precisely, they are sitting like this. Okay? Remember I said typically they are in this discrete energy level are in the gap, right? But occasionally because of this and that reason, they can get pushed down into the valence band energy level. And that can happen. And this happens in the case of NV centers. Okay, so just so you know that in the full picture, this is buried inside the valence band. And only these 3 are in the band gap. Okay? And for the most part, you can see this almost like a valence electrons. This 3-state and this 4 electrons are almost like the valence electrons, and these are like the core electrons. They don't participate into chemical or physical interactions. You can, for the most part, safely ignore them. Okay. So really, only 4 electrons matters to us. Okay. So great. Yep.
So you say the difference between n equals to 0 and n equals to positive and negative 1 is that there is a 2.875 gigahertz difference. What does that frequency describe?
Oh, that is the frequency of the electromagnetic wave. So in this case, that's microwave frequency. If you have a microwave source, say if you have a coil, a loop, okay, and you attach this to the positive and the negative of pin of a function generator. Okay, so this is called function generator. And the function generator, what the function generator does is it will have positive voltage on this end and negative voltage on this end, and it will slowly change the value on both terminals. Okay, so it's like a jumping rope. Okay, and what happened here is that the current, when this has a higher voltage potential and this has a lower voltage potential, the current goes this way, right, from high to low. But when it's opposite, so this is like an AC source, alternating current source. When this is low, then you flow the other direction, right? So so this either goes this way for a while and then goes this way. It goes like this and that, right? And this is, so when this form, when current flow in a loop like this, it creates a magnetic dipole. And the magnetic dipole has its direction associated with the direction of the flow, current flow. When the current flow changes direction, the magnetic dipole also changes direction. So effectively, you have a magnetic dipole that goes like this. Dun, 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 dun. So, and what happens? So such a magnetic dipole oscillation will result in radiation. It will generate, because the magnetic field associated with it also oscillate with it, right? So it's like you're holding a rope, and when your hand moves, the rope also moves. And what happened is that this oscillation will result in into this electromagnetic wave, and the wave will propagate through the electromagnetic field, and yeah. Anyway, so my point is, it will radiate. Okay, you will radiate photons at the same frequency as the current oscillation. So if you set the current to oscillate in a sine wave at 2.875 gigahertz, then that will be the photon frequency here, and that's what we use in the experiment. Okay. All right. Right. Yes. Right. So but now it is not. It's not a single electron transition. Okay. It is a change of configuration. Yes. So if the electron, so now we have a 2 electron. Now we have a 2 electron state, right? And this 2 electron state, when they are excited, typically they are here, so they have opposite spin. and they are in superposition. So they could be like this or this, yeah, this or this. Now, when they are excited, they will change their configuration into this or this, yeah. So it's not like a single electron being excited, but together they are excited to another configuration that has a higher energy. Yeah? Okay. All right. So, yes.
According to the M0 state is actually has lower energy than the two.
Right, correct.
When I learn Hansu, I think we learned that we will build the electron in the same string.
Has the lower energy state?
When we learn Hansu,
Mhm.
We learned that if, for example, a pre-degenerate state, we will build 3 electrons, 3 of them are still up or still down. Is that correct?
Oh, so you're talking about the p orbitals, px, py, pz, and you have this, and you're talking about this has the lower energy state than this. Correct? I think that's what we're referring to. So you're saying if I have two electrons in the valence orbital, and the valence orbital is described by this. So yeah, such as carbon, right? Then you're saying that this state has a higher energy than this state. I don't know. I don't remember that their spin state are specified. Yeah, but let's talk about that later. Yeah, I don't remember this. I remember, yes, they have to spread out. They take different seats, but I don't remember their spin state are also specified. Yeah, I always thought they are degenerate. Yeah, I always thought they are degenerate. And of course, the difference between these two, or to be more precise, the difference between this configuration and that configuration is small, okay? Energy difference is small, and it's typically called the fine structure. So when we take into account of, like tiny interactions, it gives fine structure to the spectrum. And so typically in the periodic table, we don't talk about fine structure, but in quantum mechanics, we do. So I don't know the chemistry that we learned, in high school or elementary or general physics. I don't know if that take into account of the high fine structure. I don't know, but that's, we can talk about that later after the class. All right, so this is just something that he learned in another place concerning spins. But I try to keep this material standalone and understandable. So don't worry about this discussion if you have no idea what we're talking about. Okay? All right. So yes. So when we say that this nitrogen center room temperature is a qubit, QUBIT. QUBIT stands for quantum bit. Okay, bit comes from computer science, 1 or 0. But for a quantum bit, it could be in superposition of 1 and 0. So infinite amount of possibilities. You can have 30% 1, 70% 0, or 50% 1, 30% 0, or you could have even the same weight on both states, but different phase. Okay? So So for a quantum bit, it can do much more than one quantum bit can do much more than one classical bit, and that's why quantum computing is so promising and powerful, and we all love it. Yeah. All right. But yeah, but in this course, you get to play with a quantum bit for real. Okay. So when we say it is a quantum bit, that typically implies that there are two well-defined states, and you can drive the quantum system from one state to the other, and usually one is lower in energy and the other is higher in energy. You call it this ground state and this excited state, or sometimes people just call it 0 and 1. Yeah, so this is what qubit typically represents. So qubit is a two-level system, one lower in energy and the other higher, and you can drive a transition to from the lower state to a higher state, ground state to excited state, and that is the difference between 0 and 1. Okay. So when we say NV center can work as a qubit, what do we mean? What do we mean? Here's the answer. Now you're prepared to understand. Okay. I'm gonna draw you the most comprehensive picture here. All right. So remember that we have earlier we have this picture, right? And we have 4 electrons in the lowest state, 2 states, and 2 electrons in this state, right? Yep. And I give you the number, the labels of each state. Yes? Okay. And I told you that when you have 2 here and 2 here and 2 in the excited state, that is the lowest energy configuration. Yes? Okay. So that's just put that as a note. So let's just draw this, and we will not distinguish EX from E and EY because they're degenerate, so let's just call it E. Okay, so 3 levels. Okay, so 2 here, 2 here, 2 here, 2 here, 2 here, 2 here. Yeah. So 2, 2, 2. That represents how many electrons are in each level. Okay, so this is the lowest energy state. The next energy, the next highest energy configuration is this. One, two, one, 1, 2. Okay, so you see 1, 2, 3. 1, 1, 2. 1, 3. Okay, get it? Okay, so this is the next highest, and in the literature they have names, and I'm telling you this because just in case you get so motivated and you want to read the literature yourself. The phone? Okay. Yeah, it's okay. Let's see. It has a name called this. Okay, so these are just molecular orbital names given to such configuration. Okay, and from our earlier from our earlier discussion, we know that there are more than just this. There are spin states, right? So especially we have this structure, right? So there are 3 possible configurations here. So to be more precise, there are 3 different configurations that has the same energy. But taking into account of the spin-spin interaction, then we have m equal to 0, n equal to -1, and n equal to +1. Yes? Okay? The same, I'm not gonna go into detail, but the same applies here. You can probably imagine that there are also the same story here about yep. Okay. Now, these also have names. And let me write down their names. They're kind of important. Oh no, they don't. It's just this one. Okay, cool. Good. So great. So we primarily focus on this one. And this is what we call the qubit. The ground state fine structure. In the ground state fine structure, we find states that are very useful to us, and we use them as qubits, and that's this. Okay? So this is called the qubit state. All right? So I just want to give you the full picture, and this is what we use in this full picture. Okay? Yeah? Let's take a 5-minute break, and we'll come back here. This is a very long lecture, so just in case you have difficulty understanding, there is always the lecture recording online, and you can watch it one more time at home if you want. Okay. All right. So I said earlier that this is the ground state, right? And the ground state has some fine structure, and that's this, because of the magnetic interaction between the spins. And this is the first excited state, right? And this first excited state also have the same fine structure. Okay? Okay, now I said that the qubit we want to use from the MV center is buried in this energy diagram in the ground state fine structure. So this is the qubit state we will be using. Now, in a diamond, you have everywhere randomly distributed. No. I'm just gonna draw this atomic molecule shape symbol to represent MV center. So each one is MV center, and they can have different orientation with respect to the crystal, right? Okay, we can talk about that later. But they are basically randomly distributed. And at room temperature, the the population in this energy state, and so there are effectively just two energy states. The population in the two energy states are equal. That means sun. So when I say population, I mean the MV center. So some MV center have their energy here. So this is called MV1, for example, and MV2 is probably here, MV3 is probably here. It's random, okay? According to the Boltzmann distribution, it's random. Okay, MV4, MV5. Yes, it's random. In order for us to do, okay, so if I give a blue color represent cold ground state, lowest energy state, and give red color representing excited state, then half of them are blue and half of them are red. Okay, so I have this is more, okay. So MV1, so sorry. So this is MV2, MV3, MV4. And this is MV1, MV3, and MV5. Okay? Now, suppose you want to, so since you now have an ensemble means group, you have an ensemble of MV center. If you want to use them as qubit and perform certain quantum gate operation and see the outcome, right? They must all start in the same state in order to give you a uniform result. Understand? Okay. Let me just give an example. Suppose I have MV1 in this state, and MV2 in the coast in this state, right? Now I give a microwave excitation for a certain time, and supposedly the population in this case, the probability for this qubit to occupy the ground state initially is 100% at the ground state, right? And then when I start to drive the transition with the microwave, you will do this. This is called Rabi oscillation. I will talk more about this later, but this is called Rabi oscillation, okay? So suppose I choose to stop the excitation at a certain time. Let me say after 300 nanoseconds, I open the excitation for 30 nanoseconds and I stop it, right? Then what will happen is this will return to a ground state and have a certain phase, okay? Now, if I choose to stop it a little earlier, say one, now this is a bad number, so let me just call this 200. So suppose I want to do, I stop it a little earlier, 150 nanosecond. Then I will find this MV center in the excited state, in the one state. Okay, if this is called 0, this is 1, it will be in the one state with a certain phase. Okay, and this is very different from it is in the 0 state with a certain phase, right? So besides the phase difference, it also have population difference. Okay, we'll talk more about how we characterize a quantum state later. But here I just want to say that given a certain amount of excitation, I expect certain result. And for NV2, it is supposed to be here. And I hope in my measurement, I would like to see that the signal shows the population is now in the excited state. Okay? However, there is also NV1 in the neighborhood where I eliminate the microwave radiation. And NV1, EG. So NV1 initially have 0 population in the ground state, right? And when I drive it, you also do this. Yes? And when I stop it at 150 nanosecond, what will happen is you will land on the ground state. Okay? Yes? And when I take a measurement of this, I expect to see a excited state signal, right? A signal changing from ground state to excited state. But at the same time, here I also have another signal that changed from excited state to ground state. So overall, the two signal, one give me a signal boost up, and the other give me a signal boost down. And together they make no difference. The net change in my overall signal is 0. So even though I apply this quantum operation, I cannot measure it because the change in each this is like +1, this is minus. So in terms of signals, so say if this is +1 and this is -1, in terms of change, the change in different NV center canceled. And I will not have a net measurement signal, measurable signal, right? So it is important to prepare all of them in the same state, either in this state or in this state. It doesn't really matter, but they need to be in the same state to before you start your quantum control sequence. Correct? Understand? All right. So how do we initialize? This is called initialization. How do we initialize every NV center and make them to be at, say, the ground, the true ground state? How do we do that? How do we overcome this thermodynamical distribution? How do we overcome Boltzmann's distribution and make them all 1, 2, 3, 4, 5, 6 all stay at the ground state for a while? How do we do that? How do we cool? How do we cool it without using an actual cooler? Okay? Huh? We apply the green laser, correct. But how does that work? Yes, operationally, yes, we apply the green laser. Okay? But how does that work? We'll talk about that here. Okay. All right. Right now, I already finished this electronic structure. Okay. And before we get to optical pumping, I want to first tell you about the fluorescence behavior of the NV center. Okay. And you're right, we can excite it with certain lasers. But what is the outcome? And that is important. In order to do cooling or optical pumping, we need to understand its fluorescence behavior. Okay. Let me just let me just erase this. Okay. So let me draw again. So this is called the ground state triplet. Yeah, this is called the excited state triplet. Ground state triplet, n equal to plus minus 1. Excited state triplet. Okay. Yes, fluorescence. Fluorescence means when the object absorbs light, after a while it will release light, right? When it absorbs light, it stores energy in it, but after a while, that energy will be released out. Mostly in the form of light, too. Okay, so that emission is called fluorescence. For most cases, the fluorescence light have the same color or the same wavelength as the excitation light, because as you could perhaps imagine, when I have a quantum system, right? I excited from ground to the excited state, right? The photon energy is stored in the system, and later when it releases that energy, it releases the same amount of energy. So my fluorescence is the same, has the same color as my excitation. Okay, great. So this is the typical case, but with NV center, it is slightly more complicated. Right. And let me just draw. Right. Let me just use this. Let me just use this n equal to 0, for example, because when you the first thing about optical excitation is you can only excite the electron from the same state with. You can excite it if you use a linearly. This is not super important, but good to know. If you use linearly polarized light, then you can only excite n equal to 0 to n equal to 0. You cannot do n equal to 0 to n equal to plus minus 1. Okay, the number we call this the quantum number. The quantum number cannot be changed if you use linearly polarized light. But if you use circularly polarized light, you can have 0 to plus minus 1, or plus minus 1 to 0. You can have this crossed. Okay, you can have a change in the m quantum number, and the reason is because photon has a spin of 1. Okay, but let's not get too deep into it. I just want to say that typically we use linearly polarized light, and then we excite n equal to 0 to this state. Okay. Now, there's something more. Electronically, NV center has this spectrum, but realistically, because we know that the structure is such that so remember that 3D structure I drew earlier? So carbon, 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 carbon. Yes, that's the diamond structure, right? So when we have an NV center, we typically draw the vacancy in the center, and then we have carbon, carbon, 3 carbon, and then one NV. Yes? Okay. So you can see that the N can actually pick 3 different locations. 1, actually 4. 1, 2, 3, 4. Four positions. And with these 4 different positions, the MV axis is oriented differently with respect to the crystal lattice. And that will have an impact later when we talk about Zeeman splitting and that kind of stuff. Okay, but I just want to let you know that this orientation matters. Okay, and since it's like a molecule, you can think of it as something that vibrates. And this is not hard to imagine because for all the for carbon atoms, they are in the diamond structure and it's very like rigid and solid because all 4 feet are fixed. But for this is actually a virtual bond, right? This is not like really a solid bond. This is like a virtual bond, right? So when I talk about MV molecule, don't forget that this is there's no physical atom in this location. So this bond is like a virtual bond. So you can imagine that there's a lot of movement allowed for the nitrogen atom to move in this direction. In the other 3 directions, it is fixed, but in this direction, it can move. Okay, so the vibration along the MV axis of the vibration of the MV molecule matters a lot, and this vibration in the quantum language we call it phonons. Okay, excitation of phonon modes. So what I try to say is every electronic state, that's the electron, but the nuclear motion or the atomic motion also is a quantum state, and that is that has a very very small energy spacings. Okay, from one vibrational state to another vibrational state, it has very small energy spacings. So much that together they almost form like a band and a band here. They're almost like a band grouped here and a band grouped here. Okay? Okay. Now with that knowledge, you can see that if I apply energy, and by the way, this gap is 637 nanometer. Okay, 637 nanometer. If I apply an energy slightly above that, will it work? So this is a big gap, by the way. So this is very, very small. So super, super small like here, okay? Okay, so this is like super small. So if I apply a laser with frequency slightly above this, so say like here, right? So I'm not touching that state yet. And by the way, if I use linear light, even I have energy this much, I cannot excite my electron to. I cannot excite my system to that state, right? Because n cannot change, right? But anyway, that's not my point. My point is, if I have energy slightly above this state, will the excitation still work? Normally, no, because you are outside of the resonance. You are above the resonance. You pass over the resonance, right? You drive too much. You give too much energy. You need to be just right in order to drive the excitation. However, because of this phonon band, it is possible to drive both the electronic excitation and phononic excitation. Okay? So in other words, if you drive with a frequency like this, then this part of the energy this amount of energy is going to go to the electronic configuration. It's going to go to the electronics. And this amount of energy here is going to go to the phonons. So the excitation, the vibration will get started. So not only is the electronic state become different from A1 prime 2, A1 2, E2 to A1 prime 2, A1 1, E3, not only is the electron configuration different, but also the molecule will start to vibrate. Okay, and this is called in terms of so in terms of so if we draw if we draw an excitation spectrum, okay, so this is population, and this is the wavelength. How much can, don't forget, so normally this is 673, right? So normally we can only excite if our laser is at this frequency. But because of the that it's called phonon sideband. Phonon sideband. Band. Okay? So phonon sideband. Because of the phonon sideband, the presence of the phonon sideband, it is possible to drive it with higher frequencies. Okay? Higher frequencies. Higher frequency means lower in wavelength. Okay? So, and it turns out, there is explanation to it, but I'm not gonna go into it. It turns out it peaks at about 533 nanometer. Green light. Okay? Okay, so instead of going down like this, it actually has a peak away from 633. Okay? And the reason of this is because something else. It's called Frank Condon. I'm just going to give you names. Condon principle. So if you go to eLearn, under the course material quantum spin lab, I give references. Okay, and there's a very useful thesis, PhD thesis from a student in 2017, University of Basel. So that's from Switzerland. He wrote this very, very super useful theoretical section, chapter 2, and it's all explained there. Okay, so if you're interested, look it up. But this Frank Condon principle give this shape, and it makes the excitation peak at the green light wavelength, and that's why we use green light to excite our system, our NV center. Okay, so this explains the emission. Excitation. Excitation. Okay, how about the fluorescence? How about the fluorescence? Okay, know that this mode, once NV centers start to vibrate, right? Because it's not isolated by itself, it is linked to the entire diamond structure, and the diamond bonds are very rigid, okay, hard, rigid. So they serve as a very good conductors for vibration. You slightly touch them, the energy just pass, can easily pass through the carbon bonds to more carbons. Okay, so so when you are excited, say here, it's the decay is very, very fast because the NV center is coupled to a very efficient vibrational environment through very efficient coupling. So this decay time is super fast. So once you are up there, you immediately, you basically go down to this lowest state, okay? So in principle, so now we're gonna talk about fluorescence. So even though you are excited to hear, after like so fast, the next time you check is already here. So in principle, we should have fluorescence from this energy to this energy, right? 637, right? So even though, so when we have, even though we are exciting with 532 nanometer laser, most of the excessive energy goes into the vibration modes and dissipate into the diamond lattice. The remaining one is supposed to give us this electronic energy, right? So in terms of fluorescence, we are expect to see a peak at 637, correct? That's what we expect. However, due to the presence of the photon vibrational modes, the photon side bands, also associated with the ground state, it is also possible to fall to here, fall to the side band instead of to this ground state. Okay. So there is another band of fluorescence that could occur. Okay. And it turns out this also peak a little bit away from 633. Okay, so this is mostly in the 700 to 800 region, like infrared. Okay, you can still see it, but it's dim. Okay, so the fun thing about NV center is that it takes green light, but it emits red light. It takes green light and it emits green light. It takes green light, but it emits red light. Okay, and the extra energy. So this is high energy photon. This is low energy photon, right? The extra energy goes into the phonon modes and dissipate into the diamond lattice environment. And because of this reason, okay, so now we're done with the fluorescence spectrum. Because of this reason, we can detect, okay, we can optically detect the state of the NV center. If the fluorescence is in the same color, in the same wavelength as the excitation, then our excitation light will be too strong to overwhelm our detector. Yes? So whatever signal we collect, right? So when we shine light to this NV center diamond, part of the excited light will reflect back, right? So when we collect fluorescence to our signal, the reflection from the main excitation beam will also come to our detector, and they are distinguishable, and we will not be able to tell if which is from the NV center and which is from our laser. We will not be able to tell because for the most part, our laser has much higher power than the fluorescence light. Okay, and we will not be able to determine get any useful information from the NV center since the fluorescence light is too much weaker. But now, since is emitting at a different band of strong, very distinguishable band of light from excitation spectrum, we can now use a two-color, it's called dichromatic beam splitter. We can use a two-color beam splitter that transmit one color and reflect the other color to split our signal, to kind of purify our signal from our pump excitation laser. Okay, So that's what makes it optically detectable, makes MV center state optically detectable. Okay. All right, now I'm gonna talk about the last topic, optical pumping. And this will give us an idea how to prepare all the MV center in the same state. All right, so earlier I talked about ground state triplet and excited state triplet, right? Believe it or not, there are also other states in between. Okay, there are also other states in between that I intentionally skipped, but there are also other states, and they are called the singlet states. Okay, and there are two singlet states. So singlet state means the spin orientation is also opposite, but they have a minus sign difference. Okay, that's the spin singlet state, and that's the only option, only spin state that is possible for these two motional states. Okay, these are called A11 and E1. Okay, remember earlier this is called A2, 3, and E3. The number at the top left corner, 3, this represent triplet. This represent triplet. And this 1 represent singlet. Okay? And this A and E and this number are just notations for molecular orbitals, okay, to describe its symmetry. It's not really important for our purposes. Okay, now, what I want to say is, when we excite this thing, so some MV center has population here, and some MV center have population here, right? When we excite with a green light, this will go to here. Yeah? And this will go here. Yes? Now, when it decays, the magical thing is when it is in this state, there are two possible decay paths. One is radiative, so it goes directly back to here. The other is non-radiative. Okay, it goes here. It changes from a triplet state to a singlet state. Okay, and this involves a change in the spin. So this triplet state has a spin 1. Is basically a spin 1 particle. You can think of it as a spin 1 particle, and this is like a spin 0 particle. So it changed from a spin 1 particle to a spin 0 particle. All right. And here you will have also radiative decay down, or non-radiative decay. Okay. Non-radiative decay just means your energy goes into other degrees of freedom, such as spin or vibrational, or just other degree of freedom, other channels that take away your energies. Okay. So anyway, when you excite to this state, this has a high chance to go here, and this will decay to this, and this will go here or here. All right, so the complete path is this. In conclusion, this will go either back to its original state, or it will go to the ground state. That's two paths. Okay? So ground state n equal to plus minus 1 will go to excited state, and through this, and then it will end up in ground state n minus plus 1 and ground state n equal to 0. Two paths. But for n equal to 0, for the most part, it does have a slight chance to go here, but it can be ignored. For the most part, it just go back to itself. Its decay path is dominantly radiative. Okay, so for ground state, it will just go straight back to itself. Okay, so I guess you can see what happened if I try to excite this for many cycles. Every time I have an NV center sitting here, it will fall back to this place. But if I have NV center sitting here, there's certain chance that it will fall back to itself, but there also is a certain chance that you will fall to the n equal to 0 state, right? So since everything that is here remains here, but here will always, after each cycles, there's a probability to split it to here or here. After many cycles, the outcome is everything is going to be collected. Every NV center is going to be sitting at the ground state m equal to 0. Okay. So in a sense, this is optical cooling, right? Because this is a lower energy state than this. So it cools. It overcomes the thermal distribution and make it a sharp distribution at the lowest ground state. So this can be seen as an optical cooling. Just like in other atomic systems, you cool the system down to the ground state, okay? So the technique is called optical pumping, but the phenomenon is effectively an optical cooling scheme, and then that prepare the quantum system to the ground state using laser light, not cryogenic contacts. Okay, so that's this optical pumping. Okay, so that concludes today's lecture. So today we talk about electronic structure of the NV center and how the fluorescence spectrum is different from the excitation spectrum. Okay, this is the fluorescence spectrum, and this is the excitation spectrum. They are very distinct. And lastly, we'll talk about how optical pumping using 500 nanometer light can prepare all the NV center in the ground state, which is in the n equal to 0 ground state triplet. Okay, so that concludes today's lecture. If you find it hard to follow, there is the recording. We will put recordings on eLearn and for you to replay. And so I encourage you to take advantage of that. And if you find yourself in the video and you don't like that, whatever, feel free to write me an email, let me know, so we can make appropriate arrangements so you don't show up in the camera. All right? Okay. So before we go, I have a little quiz. And the quiz is just for fun, okay? The quiz is to help you to remember. Okay, I think this might be too easy for you, but I'm gonna ask it anyway. The quiz is, number one, how many qubit states? Now this is actually a trick question. How many qubit states are there in the ground state triplet. Okay? All right? 1, 2, 3. Okay. Please stand up and choose your answer. Stand behind your answer. Okay, we have a normal distribution. So you 4 choose 2, and you choose 1.
Yeah.
And you 3 choose 3.
No, I'm being weird again. I choose the infinity.
Okay. All right. You have to convince people why it's infinity. Okay. All right. Okay. Now you have 2 minutes to convince each other. Convince your next line, and tell them why your answer is true.
Task for me. I'll convince everyone. Okay, my reasoning is there's only 2 qubit states, right? 0 and 1, excited or ground. And so if you're in the ground state already, then you're already in ground state.
You don't need to convince me. You need to convince them.
Yeah, well, that's my reasoning. Yeah, but triplets concerns electrical configuration of the electrons, not the qubits, right?
Or qubit is always in the position, but here is actually the ground state of the system. So it means
Well, what's your reasoning then? What's your reasoning then? Yeah, but triplets is how the electrons distribute, right? Like there's 2 on the first.
energy level.
Yeah, right. There's energy level.
And there is 3 states in the ground state.
But are these qubit states?
I will come with
These are how the electrons are distributed, right? That I don't.
electron spin.
Spin. Okay. But then isn't the qubit state like? Maybe you mean that lowest energy only one state fulfill the.
Can I interrupt? I love to see that you guys all discuss as a group, but I would prefer if 2 of you can pair and convince each other. The communication will be more effective.
Okay.
So if you can just grab him and grab him and grab him and then you grab her, you just try to convince the other person why your answer is correct. Okay. So why don't you come here? Here are more space. With your partner, here is space for you.
But you're on 3. So your reasoning is 1, 2, 3, right?
Yeah.
I think the
So 1, 2, 3 are different qubit states.
Yeah.
But isn't there only 2 qubit states? Isn't this how the electrons? Yeah.
Or the ground state.
Okay. 3 states for the electrons, not for
In general, we say qubit is a level system.
yeah. So how do you have 3 states? Like I think it makes sense. I think it's more of a question on the definition.
I'm sorry, interrupt again. When I say qubit state, I mean, so 2 state is 1 qubit state, so a pair. So I should probably write qubit state pairs. Okay? Just to clarify. Okay, so So when I say qubit state, this is one qubit state. Okay, qubit state pair. That's what I mean. Yeah. Okay.
No, still no. This as in.
So
This
0.
or this.
I don't care.
Okay.
So 0 and 1, right? This pair is what I call a qubit state pair. So how many qubit state pair are there in the ground state triplet? I don't want to confuse you with my appropriate use of words.
Okay. Let's say if we're at and then let's distribute it this way.
This is
Yeah, ground state triplet.
how many qubits there are there? Because
Yeah.
you want me to lay the ground triplet,
Right? Because the way I understand the
2 more minutes.
lecture is that this is one is here, one is excited. That's how I understand it. The way I see it is like, let's say, E and then G, and then this is basically, this is equals to 1, and this is equals to 0. Or is it? Yeah. It's the same, right? And so, my concern is if we're inside of this already, it's called a qubit. How can we have another side? Don't worry.
No Chinese. Thank you. You can do Chinese in the lab, but not during the lecture. Thank you.
this constant is not for qubit. It's for the system.
Pairs means they have two.
What is this?
MD center. So I think
What is in the center? One electron vacancy in the MD center is 1 qubit, right?
this virtual molecule.
Yeah.
And for this molecule, they have ground state and in the ground state, they have a triplet to form a two-level system.
Okay.
Let's draw it out.
I don't know what it is. I understand this, but whether you think one because
6, right?
there is only one.
6.
This is
Yes. Forms let's say a molecule. And so in this molecule there's
it has its own ground state outside.
Yeah.
And for the ground state, you can there is three.
yeah, the way it distributes, right? So it's like
All right, time's up. Thank you very much for your discussion and your participations. I would like you to choose again your answer out of your own will. Okay, now we have bimodal distribution. Are you guys still 2? 2? 2? 2? And 1, 4. And what about you, Marlon? Are you still staying in infinity?
He didn't convince me, but I mean, I'm not convinced of this one either. But like, I'd rather be wrong and know why than be right and not know why.
So what it would look like to be right and don't know why?
Sorry?
What would it be like for you to be right and don't know why?
I mean, he seems to know the answer. He just couldn't convince me. So like, I could just stand there. But
I see. Got it. Cool. Thank you very much. All right. Thank you, everybody. The answer is 2. Okay. Okay. So please have a seat. Please have a seat. The reason is 2. And here's the reason. The triplet has m equal to 1, n equal to -1, n equal to +1, right? They are physically different, okay? So these are physically different. Energetically, they are the same, but physically, they are different. Okay, so these are distinguishable states. And qubit state pairs involve 2. So Here's one pair, here's one pair. So the answer is 2. Okay, so that's the reason. Now, question number 2. And I'm sure this you guys will get this right. How many electrons does MV center have? Okay. Again. 3, 2, yes. All right, yes, it's 6. Okay, thank you very much. Okay, it's 6. All right, cool. Now everybody's happy because we have the last quiz right? We end at a good note. Okay, now I see we have a little time left, but let's still try to get some work done in the lab. Okay, so you're dismissed, and we can talk.